If I could have your attention, we'll get started. Welcome to the EOS Friday afternoon seminar. I'm pleased to introduce a neighbor and colleague, Dr. Ruoying He from North Carolina State University. Ruoying got his bachelor's degree from Ocean University, Qingdao, and then came over to the States and got his PhD at the University of South Florida. And from there he went up to Woods Hole Oceanographic Institution, where he was both a postdoctoral scholar and an assistant scientist in the Applied Ocean Physics and Engineering department. And then after a few years, he came down to join us here in the Triangle at NC State, where he's now an associate professor. Came down in 2006. Ruoying is a physical oceanographer and specializes in the circulation of estuarine and coastal areas. And in particular, he's been studying circulation and the modeling of that in the Mid-Atlantic Bight, South Atlantic Bight, and the Gulf of Mexico. And his work at the Gulf of Mexico suddenly got a lot of attention for a very obvious reason last spring. And there was a very nice profile of Ruoying in Nature, the June 20th issue this past summer, about his work. And he's going to be discussing the Gulf of Mexico circulation and the BP oil spill in association. So welcome, and thank you very much in advance.
Well, thanks so much, Susan, for inviting me here. We're so close by, it's only 30 minutes drive, but it took me 45 minutes today because of the traffic on the I-40. So what I'm going to talk about is something happened this summer that has been keeping lots of people very busy in a rapid response mode. So I'd like to acknowledge my funding agency, National Science Foundation, and also NC Sea Grant for their support to allow me to do this work. And also some other solutions, some other results I'm also going to share with you is coming from different projects funded by DOE and also USGS. So I was showing little photo slides before the seminar starts, but this is just a recap showing some impact of this oil spill events. So that's in the time sequencing order, so from day 1 all the way to day 49. So as well, no, this is a pretty major incident. So not only cost 11 lives, but also lead to a very large environmental disaster that we will be facing in many years to come. And this is some numbers I took from the USA Today. So this is some statistics showing by September 3rd, 137 days since the oil rig exploded, and we see that there are over 200 million gallons of oil spilled in the Gulf, and as a result, there's almost 40,000 square miles of federal water got closed. And then by early September, by September 3rd, there's more than 6,000 marine life was found dead, possibly as a result of this oil spill. So again, just some depressing numbers. I was showing these numbers to my wife, and she said she was very sad, and me too. I was very sad too. But I think as a scientist, it's also our responsibilities to be part of the relief effort by doing more research in the Gulf, and then share our scientific understanding with the coastal managers and also the public in general. So what I'm going to do today is I'm going to describe some circulation background. So it turns out lots of research has been done in the Gulf. So we have some basic understanding about the circulation in the Gulf. And to understand the fate and the transport of oil spill, we do have to have some decent understanding about three-dimensional circulation pattern. And then I will show you what happened this summer. So it turns out this summer the circulation is quite different from what we know the mean condition. And then the key question is where are the oil plumes? And I will share some information with you. And then because we're still in the hurricane season, okay, so what are the possible hurricane impact on the spill? In summary, I give you a few conclusion statements and also a few comments on the way forward. So if you think about the Gulf circulation, it's actually, we have to look from a larger scale picture, and Susan is expert on the larger scale circulation. So the Gulf circulation is actually part of Atlantic circulation system. Okay, so this is a study by Bill Schmitz in 2003, showing that the stream function, the transport of the North Atlantic circulation system. So if you focus on the Gulf, you can see that the net flow into the Caribbean Sea, so this is a continuous flow coming from Caribbean Sea into the Gulf and then become the Gulf Stream. So, but if you think about the transport, okay, so net inflow into the Caribbean Sea, there's about 45% coming from the southern hemisphere. Somebody's calling. And then the rest of the transport, about 55% is coming from northern hemisphere. I should say northern Atlantic Ocean. All right, so this is actually part of this conveyor belt, if you will. And then if you zoom in, look at the Gulf Coast, the Gulf of Mexico, we also see lots of very unique topographic features. And I should draw your attention that the Gulf is really, really deep. Okay, so it's more than 4,000 meters at the center of the Gulf. And then we have a very wide West Florida shelf. And then of Mississippi, we have Alabama coast, we have a very narrow so-called decidual canyon. Okay, and then this is where the BP, Deepwater Horizon oil rig is. And then west of the BP site, we have, again, pretty wild latex, Louisiana, Texas shelf. Okay, and then if you go to the south part, we have Campeche Bank. This is part of Mexico coastal shelf water and Bay of Campeche. All right, so and then if you think about the circulation, again, we have two major gateways. One is of Yucatan Strait. This is pretty deep again. This is 2,000 meters. And then the exit, this is Florida Strait, so it's about 800 meters. So this is very deep. The inflow is very deep, and outflow is only less than half of the depth of the Yucatan Strait. And then this has lots of impact in terms of the topographic constraint on the Gulf circulation. And one of the major circulation features in the Gulf, as we know, is loop current. Okay, so loop current, there's a very strong inflow coming from the Caribbean Sea, and showing here is sea surface temperature. So this is SST satellite imagery, showing we have this clockwise circulation. We call that loop current. Okay, so it can penetrate pretty deep in the Gulf, and then rotate clockwise, and then move out of the Gulf of Mexico to our coast, and become the Gulf Stream. And we also know that oftentimes this loop current can shed larger scale eddies. In this case, you can see very clearly this is one anticyclonic eddy west of the main body of loop current. Okay, so that's actually the eddy prior to the formation of this loop current. And then this is from altimeter, satellite altimeter data showing the life cycle. This is over, I think, 10 years, showing evolutions of this loop current. And then as the loop current moving further into the Gulf, it starts to penetrate, shedding the larger scale eddies, and eddies can propagate westward. All right, so this is the most important circulation features in the Gulf. And as I will show you later that this has tremendous impact in this event. So early study trying to understand and also quantify the shedding frequency of loop current. So this is the results taken from Bob Leland's work, published in 2005. So he looked into a 31 years altimeter data record, and the focus is on the separation intervals of each different eddies. Okay, so you can see that there's 9 different eddies in 1974, and then sometimes in 2001 you got 19 different eddies. Okay, so if you look at the spectrum jump back and forth, and so the separation intervals can vary from 2 weeks up to 18 months. So pretty large spectrum if you think about that. And then what he did is actually to do the cluster analysis. So he said we can see that the peak concentrate near 4.5 to 7 months. The other peak is at around 11.5 months, and another peak is about 17 to 18.5 months. So about 6 months apart. Okay. But the question why the loop current and the eddy shedding process behave in this way, so almost in the quasi chaotic way, has not been fully understood. So it's still an open question why there's eddy shedding, why the eddy shedding at different time scale. So that's still part of the research ongoing. All right, so let's talk about the mean circulation. So we know that the surface circulation in the Gulf is anticyclonic. So you can also see it's clockwise rotating. And this circulation is forced by both wind stress curve, and is also affected by the eddies, the anticyclonic loop current eddies. So this is actually the model simulation by Lee and George Miller in 2003, showing this clockwise surface flow. And on top of this surface flow, you also have these loop current eddies that propagate westward. Okay, so that's all the eddies as we can see from the previous altimeter data. So that's a surface condition. I think people know this for a long time, especially the fishermen. They know how to drive their boats, so they can take advantage of this very strong clockwise currents, so they can get out of the Gulf quickly. But what about the deep ocean circulation? Again, the information, I'll come back to show why this information is important for this summer BP oil spill events. And turns out the deep circulation in the Gulf is other direction. It's cyclonic or counterclockwise rotation. Okay, and the supporting evidence came from the current meter observations, the deep ocean floats, and also from numerical models. And this is a paper published by George Wesley in 2005 showing some drifter results at about 1,300 meters. So it's quite noisy because the entire observation period covers about 2 years. Okay, so it's a synoptic observation for each factor, but he's putting everything together, trying to come up with a mean condition. So it's noisy, but if you look closely enough, you get a sense that indeed this is a counterclockwise wake flow. Okay, so it's about less than, you can see this is about 5 to 10 centimeters. And then the other one on the other side, this is from the same paper by Lee and Miller et al. Showing the deep circulation at 1,500 meters. So again, model is more smoother. You do see that circulation is this counterclockwise rotating. All right, so the key information is surface, we have this clockwise motion, but below 1,000 meters, the ocean flow is to the other direction. And also some research showed that because we have this pretty deep inflow channel of Yucatan, and turns out they have a two-layer structure. So you can think about for the 200 meters, the upper 1,000 meters, the current is moving from the Caribbean Sea into the Gulf of Mexico. But below 1,000 meters, there's this return flow coming from the Gulf of Mexico back to the Caribbean Sea. Okay, the reason is because the other exit here of Florida Strait is really shallow. So basically, all the exchange between the Gulf and Atlantic Ocean is through the upper water column. Okay, so the deep exchange is between the Gulf and the Caribbean Sea.
So, Ruoying,
yes.
That displacement, you say it's roughly equivalent. On what time scale does it need to be roughly equivalent?
This is a few years time scale. Yeah, pretty low frequency.
Yeah.
So let's zoom in this East Coast, East Gulf of Mexico region. Okay, so again, this is BP sites. We're focusing on the Mississippi, Florida shelf. Okay, and again, this is very strong loop current, western boundary currents. And then we know that the shelf circulation here is driven by both local forcing, which is wind, heat flux, and all the rivers, and also driven by the deep ocean circulation. Okay, and this is right in the middle. And the question is how the deep ocean impacts the shelf circulation. Okay, so it turns out this is, I did my PhD thesis on this topic. So we can summarize this deep ocean and shelf interaction into two different categories. Okay, so category one, if you look at this cartoon, again, this is the life history of loop current. So there's type 1 interaction is happening when the loop current is in the fully developed stage. Okay, so the northern boundary of the loop current is pretty deep in the Gulf. Okay, and then in that case, we had a few measurements on the shelf and also a few ship transects. We did CTD cast of Sarasota. So this is coast moving offshore to about 200 meters. And then what we did is we take temperature salinity measurements, and then we can compute the geostrophic velocity. Okay, so we do see this very strong. Okay, this is the satellite imagery SST for the same days. So we have a very strong loop current moving around. So you even see this shelf cold water entrainment. Okay, so you see this cold water boundary, and then this is loop current moving from north to south, and you also see that this loop current moving southward for both days in June. But then there's a very clear cutoff boundary between the shelf circulation, deep ocean circulation. Okay, the boundary is right at the shelf break. So what this implies, when the loop current is in the fully developed stage, because of the very strong topographic constraint at the shelf break, all the deep ocean forcing is confined in the deep ocean. Okay, the loop current influence is confined in the deep ocean. So the shelf circulation is largely determined by the local wind forcing. Okay, so the topographic constraint provides the barrier in this type 1 condition. There's another case. If you look at this cartoon, again, whenever this big eddy shaded, the loop current will retreat to the south. At that point, the loop current actually start to hug the southern tip of West Florida Shelf. And if you look at this isobath distribution, that you see that at this location, this is west of Florida Keys, we have this convergence of isobaths. What happened is, whatever pressure perturbation caused by the loop current can now easily get on the shelf. Okay, and then they can propagate into the shelf interior as the coastal trap wave, which can in turn set the shelf circulation in motion. All right, and then this is a real in situ measurements, current measurements we did when it's at station A, which is about 50-meter isobath of Sarasota. And this is another station, ADCP station we did of Panama City at 30-meter isobath. So you see that when this happened, so this is in 2008, the loop current retreat. And in the meantime, we see a very strong and also unidirectional shelf circulation. So they all flow southeastward during this retreat phase. All right, so just keep in mind there are 2 different types. And I will come back to tell you why this is important for this year as well. And turns out in this year we have this type 1, type 2 happened in summer 2010. All right, so that's the basic background information about what we know about the mean condition of the Gulf circulation. So what happened this summer in 2010? So one thing we try to understand the circulation in this summer is actually using numeric models. At NC State, my group is actually running an operational ocean forecast model for the entire Gulf of Mexico and South Atlantic Bight. Okay, so the model covers the entire region, and showing here is the model predicted sea surface temperature in winter. This is this is April 2004. So at least some key information about this numerical modeling system. So it's about 5 kilometers spatial resolutions, and we have 36 vertical layers. So it's a fully 3-dimensional model. And this model is actually nested inside global ocean model. Okay, so in that case, we can start to simulate pretty realistically about all the western boundary currents, right? So you can see the loop current, and you can follow this temperature contour lines to see this is becomes the Gulf Stream, all right? And then here we are in North Carolina, and then this is Outer Bank, not too far away from the mainstream of Gulf Stream. So we're using realistic surface forcing. This is from NSAP NAN. And we also consider major rivers, Mississippi rivers, or other major rivers in the southeast, and also tides. And we also use turbulence closure scheme, trying to compute the vertical mixings. All right, so that's the modeling system we have been using, and we're running this. We start running this ocean weather we call ocean weather nowcast forecast starting in 2008. Okay, so we didn't know this BP oil spill would happen. We just has been running this for scientific purpose. Okay, and then every day we run this nowcast forecast. So we run today's nowcast. We also provide the future 3 days, 72 hours ocean forecast, just like meteorologists will do for weather forecast. Okay, so we have been doing this for 3 years, and then this oil spill things happened. And this is nowcast forecast. So one of the image we actually post online on daily basis. So this is an image we post online for June 9th, 2010. So showing here in color, this is sea surface height, okay, and the black vector here are sea surface velocity, and the purple vectors are surface wind from inset, okay. So I'd like to draw attention that we have a huge eddy. The eddy is so huge that people even gave him a name called Eddy Franklin. All right, so this eddy is about to pinch off from the loop current. All right. So this is actually in the middle of the BP oil spill. This is in June. The oil spill started April 20th, not being capped until July 15th. So this is actually in the middle of the event. And I will tell you again later that this eddy is playing a major role in terms of the plume transport. So this is one of the many images we post online on daily basis. And the other thing is, since we running this system for 3 years, and we keep posting all the model solutions online, we actually serve the output on an open depth server, so people can go there and download our solutions. So it turns out to be quite useful for NOAA. So NOAA actually went to our website and download our daily nowcast forecast 3-dimensional circulation fields. And they have their own oil spill plume or oil spill trajectory prediction model. Okay, so they use circulation model as a feed to take surface velocity fields and then run their the oil plume trajectory simulation. And they did this in an ensemble way. Okay, so they used 4 different circulation models. There's a Navy model, NOAA model, university models, and also NC State models. And then they can come up with this envelope. Okay, so this is almost like uncertainty boundary, because different models give you different solution. But by running 4 different circulation models in conjunction with their plume trajectory, they can come up with uncertainty to show where they need to, say, deploy ships, deploy aircrafts to do the samples. Right. So we're quite happy that we're able to contribute in this rapid response event. And then early June, we also got support from National Science Foundation as part of the RAPID program. So what we propose to do is to provide a more detailed circulation study using this what we call SAPGOM circulation model, and then couple that with a tracer model to study not only the surface, we also want to understand the subsurface distributions of the oil plume. And specifically, we try to see how is the spill is distributed at different depths, and to what extent they have been transported. And secondly, how does the strong mixing associate with tropical storms? At that point, in June, we're still thinking there's the chance that the strong hurricane will come to Gulf. So what happens if there's strong mixing? And finally, what is residence time? How long the oil spill will stay there? So that's the scientific goal we're trying to address here. So then we came back. We actually used the model. We fine-tuned the model, did a circulation handcast. So we're trying to reproduce the conditions that happen in the summer. So again, the color here is sea surface height, and velocity black vector here showing by the black vector showing the surface currents. Okay, so this animation we actually did the handcast from April 20th to the end of July. And you see that initially we have a very healthy, well, this is already in June, but initially we have very healthy loop current penetrating into the Gulf. And then at a certain time, this eddy becomes so large that start to pinch off. and then become a separate eddy, and then this loop current will retreat to the south. Remember the type 1, type 2 deep ocean and shelf interaction. Okay, so over this past 4 months handcast period, we have both type. Okay, and again, what's happening is we have a huge eddy sitting between the BP oil spill sites and the very energetic loop current. So we have these three-dimensional circulation solutions saved on hourly basis. Well, we can start to understand more about the circulation dynamics and the transport implications of the oil spill. And again, this is become one of the national emergency events. So now I'll put lots of effort trying to collect different kinds of observations. So showing here are this is airborne AXBT surveys they did in the Gulf, basically focused on the loop current region. So what happened is they dropped these sensors that can measure the upper 400 meters temperature structure. So that's one type of observation. And then there's a lot of ship observation, and there's more than 14 different ships doing surveys. I'm only showing a few examples. So they're doing more concentrated surveys, and also they're doing surveys in the nearby coastal waters. Okay, and then there's a different AUV underwater vehicles. This is so-called glider surveys. 10 different deployments. Some of them are surveyed in the BP sites, and then there's also survey in the Florida sites. One of concern was what happened if some oil spill can get on the shelf of West Florida. So they did lots of deployment in this region. And also there's some Argo floats. So Argo floats are being used to track the deep ocean circulation. And also every 10 days, Argo is coming to the surface and give you temperature salinity profiles. So all of a sudden, there's lots of observations in the Gulf as results of this event. And there's also another data set called coastal current surface cold currents. So what happened is there's 3 different HF radar that transmitting audio signals, radio signals to the ocean surface. Okay, so one radio sending signals out to the ocean, and the other radios receiving the signals, and then basically it depends on the Doppler shift effects. They can give you an estimate of how fast the surface current is moving, either towards or away from the antenna. And then together they can come up with a surface map. Okay, so this is just animation. This is coming from the Janku's part of the Coastal Ocean Observancy, showing the surface circulation convection northeast of the BP sites. Okay, so this actually becomes quite important for the coastal managers to determine which close, where they need to close the beach, etc. So I'd like to show some observation comparisons. So we actually collect all these observations, different kinds of observations. So we see we can start to do pretty vigorous model data comparison. How useful these model handcasts we have, how realistic they are. Okay, so I'm going to show a few examples. So this is a glider transect. So this glider moving southwest of the BP sites all the way to the center of the Gulf. So it's measuring the upper 1,000 meters temperature fields, and then the salinity fields. So this is one of the scripts. Spray glider can go pretty deep, measuring the upper 1,000 meters hydrographic condition. And then this is our model handcast solution on the same day, actually, along the same track for the same period. So we see that model is able to capture the upper thermal structure quite nicely. And salinity-wise, we're able to capture the surface freshening, and then there's also low salinity, relatively lower salinity below C300 meters. But we also see the model has about 0.5 PSU offsets. Okay, so that's one of the limitations we are realizing.
Right. Is this your model's a forward model only, or are you assimilating any? It's forward only.
There's a forward
external
only.
Force. Okay.
Yes. Yeah. So it's forced by open boundary surface forcing. We're actually working on data simulation now. Yeah. So this is forward model. So we're trying to see how well, what's the skill of the forward model. And then this is comparison with AXBT survey. So they did 8 different transects. So 7 east-west transects, and then 1 north-south transects, And then, as I mentioned, for the upper 400 meters, along each transect, you give you this temperature structure. Okay, and then we did the same thing, sampled our virtual ocean, come up with modeled temperature, and then we compare with the basic upper ocean thermal structure. We get the idea the model is on track. Here's another comparison we did with the ship observation. So this is a one CDD cast right at the BP sites. Okay, so showing here, this is temperature profile. The solid line, this is from the ship CDD cast, and then the dots are from the model simulations. Okay, so we see we're doing a very decent job for temperature. Again, for salinity, we're about, again, 0.5 PSU off. Okay. And then this is another way to summarize all the comparisons. So I should again draw attention that over the past 4 months or so, because there's so many ships doing the same surveys, all of a sudden we have more than 400,000 temperature salinity data in the Gulf. Okay, so provide tremendous measurements to monitor what happened in terms of hydrographic variations. So then one thing we could do is to do this one-to-one plots. Okay, so we can sample model solution at each of these locations over the entire water columns, and then plot them against observation of the model together. So that's the temperature fits, that's the salinity fits. So we see that temperature, again, we are almost 101 with a pretty small variance, but then salinity we see that there's lots of variance. Okay, and again, if you look at the mean, we are about 0.5. Okay, so that's what we can tell about without data simulation. So that's the forward model scale in terms of resolving hydrographic structures. Susan, you have a question?
Fortunately, in these waters, temperature dominates density.
Yes.
So that's why your circulation features. Okay. So
exactly.
So salinity can almost be a little bit of a passive tracer.
Yes.
Okay.
Yes. Exactly. That's the point actually, thank you. Yeah, that's the point I'm trying to make here. Okay, so another comparison. Again, I'm trying to show some comparison first before we dive into the oil tracer stuff. And then this is, as I mentioned, that there's HF radar measurements by 3 antennas. So the blue vectors are a snapshot of the coastal currents. Okay, at this point they are moving towards northeast, and then all the white vectors are from our model SATCOM solutions. Okay. So we have a number of this kind of overlap map to show how well we're able to resolve the surface currents. And the conclusions, we're doing, again, pretty decent job. Okay, so in this case, they're on top of each other. And then this is now predicted the surface oil plume. So this shaded area is coming from now oil slick prediction. All right. Okay, so let's actually, this is for the same day. This is a zoom in version, and this is same day, July 16th. Looking at the entire east part of Gulf of Mexico. Okay, what I like to draw attention is we know there's large eddy called Franklin, and now the mainstream of loop current actually retreat to the south. Actually start to interact with the Florida Keys, the west of Florida Key region, and now you start to see this mid-shelf circulation. Okay, and remember this is what we call type 2 interaction. So you start to see some mid-shelf circulation, which potentially can move things around, even without the loop current eddies. What about drifters? And again, as I mentioned, there are lots of drifter observations. So this is a drifter released by USF. This is on about 1.5 months. So the drifter started, again, the purple vector, the purple color, purple lines. So if you follow these lines, you see that this is again get entered into the loop current eddies, and then make a full circle, and then moving along the short break, and then actually this one made into the Atlantic Ocean. Okay, and then this is what the model predicted, drifter trajectory, and again made a full circle, and then there's some discrepancies, but then basically follow a similar trajectory. Okay, so that's one comparison with USF drifter. And here's another comparison with Coast Guard drifter. So let me show you. This one is even interesting. So released on May 26th, actually maybe 28th. Yeah, this should be 28th. So if you follow me, and then this drifter made one loop, okay, and then made a second loop, and then for some reason decide to move northward. Okay, and this tells you how tight this loop current eddy is, and very quickly spin. And then the model solution shows similar evolutions. So you see one loop, and then two loop, and then loose steam for some reason didn't make it onto the shelf. Okay, but overall, if you look at the deep ocean gyre circulation, the model is capturing that one. There's a difference in terms of magnitude, but then it's very nicely follow this loop current eddy structure. As you move closer to the shelf, we start to see a larger discrepancy. So the model is following the observed drifter quite nicely initially, and then there's a divergence somewhere later in the deployment. If you're near the coast, again similarly, there's some nice agreement initially, and then there's some discrepancy. And remember, this is based on 5-kilometer model. Okay, so there's lots of other processes we're not resolving, especially as you go towards to the shallow water. There's surface wave, there's coastal settings that is not being well resolved by the model. But I think this kind of comparison gives us an idea how much we can utilize this 3-dimensional ocean circulation model to help us interpret the transport. All right, so let me move on. So where are the oil flow? I think this is actually one of the most important part. And I'm going to show you two different ways to represent this. One is through the Lagrangian point of view, and the other way is through the Eulerian point of view. So we are focusing on the tracer in the second approach. So the first one is on the particles. And Lagrangian, so we can start think about each oil droplets as the particles. Okay, so they are being transported by the ocean circulation. Of course, they also mix with other background. But let's suppose they can be treated as a particle or passive particles. And then we can think about their transport over, suppose, the same time period we did the ocean handcast. So April 20th to July 29th. And I'm going to show you two different solutions. Okay, so one scenario is we release particles at BP, Deepwater Horizon site, over the entire water column. Okay, and the second case we're going to focusing on the subsurface plumes. In this case, we'll only release particles up to 100 meters. And I want to draw attention that we haven't considered the chemical and biological reactions yet. Okay, so we're going to show you at the first order how the circulation is going to move things around, which actually is the dominant sense. All right, so here's animation. This is BP sites, so releasing over the entire water columns. And these next two panels really just adding the bathymetry settings in the background, and this is a zoom-in view. Okay, so you see that there's a lot of transport. It's moving back and forth, and then you see a small amount of particles moving to the east coast, and you see that because of these large eddies sitting right here, the significant amount is actually rotating in the clockwise. Okay, so instead of moving this way, they actually stay in the Gulf, do these rotations. Okay, and then if you focus on this panel, this is 3-dimensional view. We can look at this again. So you see the particle moving southward. Some of actually can go to pretty deep, and then there's a number of them follow the loop current. This is actually before the eddy got shedding. Okay, and then you see for the particles coming to our coast, they're all at the surface. Okay, because as we mentioned, the depth across these transects is very shallow, 800 meters. So all the entrainment happened in this region is just at the surface. Okay.
What was the depth of the waters at the release site? 1,000 meters?
1,500 meters.
1,500 meters.
Yeah. Okay, and then the other feature I'd like to draw attention is look at this Yucatan Strait, and you do see some particles was able to go back to the Caribbean Sea. Remember there's the two layers surface moving into the Gulf, and there's some weak return flow, and you do see a number of particles potentially can go back to the Caribbean Sea. All right. So, but this is a 3-dimensional distribution as results of ocean transport. And one way we can do, suppose we can convert all the particle numbers into relative concentrations, so we can get an idea how much really end up to our coast. Okay, so what we could do is we actually divide the entire region into 1 by 1 degree by 1 degree boxes. Okay, so we know the total number released over the entire 4 months. And we can also, by the end of July, this end of our simulation, we can count the numbers remained in each 1 by 1 boxes over the entire water column. And then you can come up with a percentage as a way to say relative concentration. Okay, so you see the majority by the end of, this is after the oil spill has been capped. Okay, so by the end of July, the majority still stayed right here. Okay, northeast of the Gulf. And we do have some get to our coast, but if you look at the number, it's less than 0.1%. Okay, again, they're only at the surface and at pretty low concentration. Majority is still right here, and also you get sense that there's a bifurcation points, right? So there's some particles moving that way, but majority is still contained by this loop current eddy, so still stayed in the Gulf. All right, so which is very nice actually. Otherwise, without this eddy, you can imagine we'll get a lot more our coast, and so one fortuitous ocean contribution to the human societies, this eddy is actually, the timing is great. All right, so what about the subsurface? So let's focus in on the 1200 meters, and then this is only just one point south at the 1200 meters, and then we can start to look at the plan view, just horizontal distribution, and also the vertical distribution. This is again in the with the bathymetry background, and you see that they're not moving as fast as surface drifter, of course, because the deep ocean circulation is much weaker, and then still they feel the impact of the loop current eddy. So you see that some of them is doing this clockwise rotation, right? Even at that depth, and then by the end of the simulation, we can do similar kind of tracer analysis, and we see that they are pretty much still in the Gulf. All right, they're almost none made into the East Coast. All right, so the deep ocean concentration is still limited in this region.
So when the oil wasn't it spilled at the floor? So isn't this the second one a more realistic simulation then?
Mm-hmm. Okay. Well, actually, because they put so much dispenser, so initially when the oil coming up, it got disturbed, and then at the 1200 meters, it started to come back again. Okay. So that's why I have a few slides to show you later why this becomes so important, because initially you don't have a organized plume, so just lots of bubbles, lots of droplets, but then a few hundred meters, so the depth is 1500 meters, but then go up to 1200 meters, they start to form again to become the oil plume. So that's why our focus now is at 1200 meters, 1000 to 200 meters, 1200 meters. All right, so let me move on. So that's the particle view, so Lagrangian point of view. What about tracer? We can also use tracers, and in this case, we're not going to talk a typical tracer. We're actually going to talk about water age tracers. Okay, so suppose this is the input source. You can think about this as BP, Deepwater Horizon site, and then there's oil droplets, there's water parcels leaving the sites, and then suppose this is the time. If you use this time minus the time when they first enter the system, that's what we call our age. Okay, so suppose you have this control volume, you can think about this entire Gulf of Mexico, and then we only focusing on this period, so we can get idea how long the water parcels or the BP oil has been in the Gulf water. So it turns out this can be solved in the numerical framework. So you have a typical tracer equation, just plus this agent term. So this tau here is what we call water age. And this is only mathematics slides I'm going to show, but actually there's a lot more behind this. But I'm going to jump into the solutions. Again, this is a tracer simulation, actually the water age simulation at different depths. Okay, from that approach I just talked about. So this is surface distribution. So you can look at the distribution, get idea where the oil plume might be. Okay, but also if you look at the color bar here actually stands for how long they have been since their first release. Okay, so we're looking at the surface, and this is at 200 meters below the surface, and this is 500 meters. This is 1,200 meters. Okay, so you see that because we have this BP site, this is before the oil has been capped. So we have a very fresh water coming from the BP wellhead, and after the well has been capped, and then of course the water age will become older and older. Okay, so so this gives you a sense about how wide this has been spread spatially, and also how long they have been in the water. I'd like to focusing on this pattern first. So this is okay. So this is actually the last snapshots showing that this is total distribution. Okay. So by the end of July, see the water now here in this region, because the well is capped on July 15th, right? So this is about near the BP sites is about 10 days or so. Okay, but as you go further away from the BP sites, the water is actually getting older and older, which is as we expected intuitionally. But this water age, that has a three-dimensional distribution. So if you look at 1,500 meters, you see that again, there's two different trajectory. One is moving westward, the other is moving southeastward, and they're also getting pretty old as they are transported by the ocean. So what we can do is, suppose we have a water sample. Okay, we know the station number, we know the dates, long locations. We can start to go back to sample these fields to come up with an age information for each sample. And this information can then be used by biologists or chemists to start infer the biodegradation rate or chemical degradation rate. All right, so I think this is quite important, quite useful information that we can offer from the circulation point of view. So now the oil has been capped. Okay, we are already in October, but there's still a lot of effort ongoing in the Gulf. The effort now is trying to find the subsurface plume. There's a number of papers. I think there are two papers in Science recently talk about there's still pretty significant amount of subsurface plume. So the method that people are using is really trying to use a CTD cast. Okay, so not only look at temperature salinity, they also look at the dissolved oxygen. So indicated by these red lines, this is the dissolved oxygen signals, and they also look at this is fluorescence, the black lines, the fluorescence. Okay, so what's happening is, suppose you have the oil at this level, and because of this biodegradations interaction, they consume oxygen. Okay, so you start to see some oxygen deficit signal. And at the same time, because you have this hydrocarbon, it also comes with a certain C-down fluorescence signal. Okay, so when scientists see these two signals, the DO deficits, this DO anomaly, negative anomaly, and this fluorescence positive anomaly, they're using these two information to identify the subsurface oil plume location. Okay, so they actually do this kind of CTD cast at a number of stations and try to trace down the subsurface distribution based on DO and fluorescence. Okay, so this is what I was mentioning about. So they have this survey grid. So at each of these dots, they do a CTD cast. And then the color here represents dissolved oxygen anomaly. Okay, so if you can read, you cannot read, I'm sorry. What happening is this yellow color means a stronger oxygen deficit, okay? And so if you follow the yellow color, okay, or even the red colors, yellow color means even larger deficits. You can get a sense that there's a plume of DO deficits. Okay, so moving west of the wellhead, okay, actually moving pretty far westward. Now it's this is actually end of end of August. So this DO plume, which is used as a proxy for the subsurface plume is already moving towards pretty far away into the west. Okay, and that's real. Okay, and then this is what our model is predicting by the end of August. So we're also seeing this westward motion subsurface plume at the same 1,200 meter depths moving westward. And as I mentioned, the color here stands for the age. Okay, again, we see that the plume at this location is about 60 days, okay, 70 days by the end of August. And then for all the plumes west of, say, south of Mississippi, and then the plume is already 3 months old. Okay, so this is end of August. So if you look at spatial pattern, okay, this is in a very good agreement with all the sampling results we got in situ. So we have been communicating back and forth with a few scientists, the chief scientists on the boats, trying to use this kind of information to guide them do more subsurface plume. Quickly, let me actually just see one thing about hurricanes. So we know NOAA's predicting this is very active hurricane season. We know there's already 17 different named hurricanes already. But fortunately, none of them made into the Gulf of Mexico. All right. So, but we do know from the past. Suppose we have a strong hurricanes in the Gulf, and they have a different impact. So in 2008, for instance, there's Hurricane Gustav, there's Hurricane Ike, and when it's a very strong hurricane, Gustav is much stronger than Ike. Okay, and has a much larger translation speed. And what we did is look into the mixed layer depths. Okay, it turns out that this weaker but slower moving Hurricane Ike can disturb the upper ocean mixed layer depths much more significantly. Okay, so the conclusion here, just in short, is that it doesn't really matter if it's strong or not. Actually, the time, the duration matters. So if it's a slow-moving hurricanes can cause a lot more mixing, potentially can bring the subsurface plume to the surface, and then the storm surge induced by hurricane potentially can move this newly surfaced plume onshore. Okay. Let me skip this one. Let me go to the summary. Okay. So the key take-home information is the look at eddy dynamics in summer 2002 makes the entire Gulf circulation transport much more retentive. Okay, so our results, both model and observation, shows that most of the BP oil spills stayed in the deep ocean, deep Gulf, far away from the coast. So which is very good news for us. Without this eddy, we're probably facing a different environmental impact scenario. But we should also keep in mind that there's a significant amount of oil on the surface. Lots of effort are being put into this. And I guess we still have 1 month away, right, by the end of hurricane season. So we should still watch out for the hurricanes and their associated mixing and transport. Very quickly, so early August, so NOAA, the government agency, released this Deepwater Horizon oil budget. Okay, so this pie chart, if you look at, let me just run this very quickly. So we see that they're concluded there's only 25% left in the Gulf water. So there's about 25% got evaporated into the atmosphere, and then there's natural dispersed and chemical dispersed, and also there's other components by other portions actually got this recovered and also burned and skimmed. Okay, so their conclusion by this report is only 25% left. And actually, I think the scientific community now disagreed with this conclusion. I think more and more evidence shows this is not correct numbers. So this is my final slide. So I think there's a number of assumptions, significant uncertainties that's in this report. And even if we accept the assumption that there's only 25% left in the Gulf, there's still about 1.3 million gallons in the water, barrels oil in the Gulf. So that's equivalent to 5 Exxon Valdez plume. So that's still a very major oil spill. Okay, and then there's lots of unknowns, such as how much this oil got biodegraded, and then over what time scales. And then how about dispersant interaction with oil spill? We know there's a huge amount of dispersant got put into this in the Gulf water. And then we also know there are significant amounts now get into the sediments. So what are the fate of the oil in that sediment layers? So just a very basic comments on the way forward. I think it's critical that it's not over. So I know the news medium don't report BP spill anymore, but it's not over in terms of scientific study. So we still need to establish a very comprehensive long-term research program so we can better understand the ecological impact. Not only in the Gulf water, we actually now should look into all kinds of chemical, biological, physical changes from the wetlands all the way to the deep ocean sediments. So with that, I will stop and thank you so much. And
thank you, Ruoying.
Yeah.
Are there any questions?
So I don't know what the characteristics of this particular oil and how naturally buoyant it is, but from your models, it seems like we've been fortunate in that it happened at 1,500 meters, so it wasn't in that faster upper circulation that would have taken it quickly into the Gulf Stream. How quickly is the oil rising?
well, yeah. Well, this oil is very different from surface spill. Okay, so this is coming from 1,500 meters below the ocean surface, so it has a huge pressure associated with this. So what happened is, and as soon as this got released from the wellhead, the nature of this oil spill is it's not buoyant actually. So some of them can, like bubbles, they can go very quickly to the surface, but because they're also under this huge pressure interaction, and also don't forget BP put lots of dispersant right at the wellhead. So the whole thing, the two things together change the nature of this oil. So some of them, well, observation shows they actually stay at this level because that's a density still. Density property got changed, and they prefer at this level, stay at this level. So I think the general public will think, oh, I should floating right to the surface, right? But in this case, because of the combined interaction between the huge pressure and also dispersant, the buoyancy property actually got changed. So that's why we're still seeing lots of subsurface plume at this level, because the 1,200 meters is actually the preferred density isopycnal layers that's actually associated with the oil plume density.
Sarah?
Do you know what influences the size of the eddies that pinch off from the loop current? Like, why was that? Is there any reason why the Franklin eddy was particularly large?
No, we don't know. I mean, as I showed early on, the entire eddy shedding process is still very much an open research question. So there's different papers talking about different hypotheses. There's wind-driven components. There's this topographic constraint. There's also this upstream inflow transport mechanism. So I think we have to go back and look at all the meteorological conditions in upstream transport to see why eddies this size is shedding at this time. But I think, as I mentioned, from the oil spill perspective, this eddy is very timely.
Yeah.
It's very timely. But why and how the whole life history of this eddy, I think, still deserve a lot more study.
Nicola, you had a question. But wait, wasn't it Eddie Franklin, not Franklin Eddy?
You're right, Eddie Franklin.
Yeah.
Okay.
Just to follow up on Elena's question, you saw some pictures of birds covered with oil. So some of it made it to the surface.
Yeah.
Is that minute amounts? Do you know what the proportion? Do you have any estimates of that?
I don't, but I think this report has mentioned. Well, they don't. No, I don't have a exact number on top of my head.
Good.
Yeah, but at this point, they cannot find any surface plume anymore.
Mm-hmm.
Okay, so They either got recovered, got burned, or got skiing. So the picture for the birds, I think that's just during the initial early stage of oil spill.
And just another quick question: how does it affect this change in buoyancy? How does it affect your age model? And what's the uncertainty on the age?
Yeah, good question. Yeah, so that's something we're trying to better quantify. Yeah. So due to the time limits, there's actually a lot more age calculation. So we can actually start to parameterize all the biodegradation stuff into this age model. So not only we can give you the circulation relevant age information, we can also provide more age information with both physical and biological and chemical processes included. So that's actually a work in progress. Yeah. Bruce, you have a question?
So in the previous slide, you're showing that spike in the fluorescence in the oxygen. And then the other component that you were just mentioning is the age.
Yeah.
So in the open ocean, one tracer for age is carbon, carbon-13, which you can see changing as the water is aging.
Yeah.
Now, this obviously wouldn't have enough time to do that under the normal circumstances, but you're oxidizing all of that oil.
Yeah.
Has anyone found a carbon signal that would coincide with this, which would give you an age?
Yes, I think they could if they do that analysis. Yeah. I don't know who is working on that right now, though. Yeah, but I think that's a good point.
It might show up.
Might show up, yeah. So just on the topic. So this is all the bacteria, that so-called oil lover in the deep ocean, that's actually consume the hydrocarbon, start to consume the oxygen, so you can start to see the deficits. So actually lots of them. Yeah, so that's why there's another dimension, this biological interaction dimension that we need to study.
Okay, well thank you. Let's thank
Thank you.
very
Yeah.
much.